Okay, in 6.5, we continue our study of related rates, but this time we concentrate on problems involving area and volume. And I guess the first thing I want to mention is you're going to encounter in this section the use of formulas for volume of a sphere or surface area of a cylinder. I do not expect you to memorize those formulas, so when you go to preparing for your exam, you should be concentrating on knowing how to do the problems. I will provide you with any formulas you need. So in the first question, this would be a relatively straightforward question. We have the area of a circular oil slick on the surface of the sea is increasing at a rate of 150 meters squared per second. So what's happening is someone has unfortunately spilt some oil, and the oil is in the shape of a circle. Now in reality, of course, the oil slick would be a little bit more irregular in shape, but that would be a bit more advanced from what we're doing. So we have to keep it simple, and we're going to look at the circular oil slick. So what's happening is the area is increasing. So what's changing is the area of this circle is changing. So we're going to need a variable for that. So we could say A is area. How fast is the radius changing? So obviously as the area increases, then so is the radius going to increase. So we're going to need a variable R for radius. How fast is the radius changing when the radius is 25 meters? So we set these up the same way we set up the related rate problems in the previous section. We first of all identify what's changing with time, in this case area and radius, and then we identify our rates of change. So we're told that the area is increasing, so that would be the rate of change of area with time, so dA dt, and that would be 150. And then of course there must be a rate of change we're trying to find. In this case it's how fast is the radius changing. So the question wants us to find dr dt when the radius is 25. So that's how we would set up this problem. Now just like in the previous section, we need a formula to differentiate. In the previous section it was often the Pythagorean theorem. In this case it's going to be a known formula that again you do not need to memorize. So in this case it's the formula that relates the area of a circle to its radius. So the area of a circle is a function of its radius. The area is equal to pi r squared, our formula for area. And so we're going to use that formula to find the rates of change. So the next step, of course, is to differentiate with respect to time. So we take the derivative of area with respect to time. The derivative of area with respect to area would just be 1, and then our compensating term would be dA dt. So this is just going to be dA dt equals, pi is a constant. The derivative of r squared is 2r. So this would be 2 pi r times our compensating term dr dt. And so there's our differentiated formula. Just a point of interest that you might find kind of intriguing. You may recognize 2 pi r is the circumference of a circle. It turns out that the circumference is the derivative of the area. The second branch of calculus that you might study someday is called integral calculus, which deals with area. It turns out that if you took the integral of this function, you'd get back to here. That's where these formulas actually come from, is from integral calculus. So the rest of it's just number plugging. We know that dA dt is 150. 2 pi times r, which we were given as 25, dr dt. Solving for dr dt, we just divide 150 by 2 times pi times 25, or 50 pi, and our answer would be 3 over pi, which is approximately 0.95 meters per second. So as this oil slick spreads, the area is increasing at a rate of 150 square meters every second. The actual radius of the circle at that moment that the radius is 25 would be increasing at about almost a meter a second. Okay, in our next example, we're looking at a triangle. And what's happening in the triangle is the height and the base are changing with time. And the question is asking, what would the overall effect be on the area? So again, in this case, a picture maybe not that necessary, but what we have here is a triangle. The two quantities in the triangle that are changing are its height, which we can call h, and its base, which we can call b. And the other quantity that's changing, of course, is the area, A. So there are three things in this question changing, so each one has to be identified with a variable. When we write out our rates of change, we're told that the base of the triangle is growing at a rate of 6 centimeters per second. So dB dt is 6. The height is shrinking, so it's decreasing, so dH dt would be -5. And the question wants us to find the rate of change of the area. So we want to find dA dt when the base is 20 and the height is 16. Our next step is to find a formula that relates those three variables. Well, that would be the formula for area of a triangle, which is 1/2 base times height. Now, the reason why I've selected this question is because there's two variables on this side of the equation. And in this case, we need them both because both rates of change are given to us. So we don't want to try to eliminate one. We have to know how to differentiate a function that has a product of two variables. So we're going to have to use our product rule. So to differentiate this, we would take the derivative of a, which would be 1 times the compensating term, dA dt, equals, the 1/2 is a constant, so I'm just going to remove it from the function. And now you have to recognize here that you have a product. You have base times height. So you may recall the product rule. It's been a while since we used that, but the product rule says that if you have a function p times q, the derivative is p prime times q plus q prime times p. So we're going to use that rule here. The derivative of b would be 1 times dB dt, the compensating term. We're always doing implicit differentiation here. But then we have to multiply by height because of the product rule, plus the derivative of height, which is 1 times the compensating term dH dt times b because of the product rule. So there is our differentiated function. Now to solve this, we have all the information we need to know. We need to know the rate of change of base, the rate of change of height, and the height and the base. All of the information is given to us. So now it's just a matter of plugging those numbers into our formula. So dA dt will be 1/2 times the rate of change of base, which is 6, times the height, which is 16, plus the rate of change of the height, which is -5, times the base, which is 20. So we're going to get 1/2 times 96 minus 100, which is 1/2 of -4, or -2. Be very careful with the units. I do insist that they're included. In this case, it's area changing with time, so it would be centimeters squared per second. So sometimes you'll have more than one rate of change given to you. In that case, you need to keep both of your variables in play in the question. In the case of an area formula, it requires the product rule. Okay, this will be our last example on related rates. This is also another volume question. This time, gravel is being poured onto the ground at a certain rate, 180 cubic meters per hour. As the sand hits the ground, it's going to form a conical pile. So the sand is going to land and form a pile in the shape of a cone, which kind of makes sense. So there's our diagram. The variables that are changing in this case With a cone, the variables that are in play, you have the radius of the base, r, you have the height of the cone, h, and of course the volume, v, would be all the things that are changing as the sand piles up. We're told that the sand forms a conical pile with the height 1/3 the diameter. So we're also given that the height is always 1/3 of the diameter d. So first of all, let's identify our rates of change. We're told that the sand is being poured on the ground at a rate of 180 cubic meters per hour. That's a volume changing. So dV dt is 180. How fast is the height of the pile changing? So the question wants us to find dH dt when the radius of the base is 6, when r is 6. The relationship between the variables is a formula that's a known formula. It's the volume of a cone. The volume of a cone is 1/3 pi r squared h. Now the reason why I've selected this question is, you remember in the previous one we had two variables, but we needed them both because we were given both rates of change. In this case, if we were to differentiate this formula right now, which we could do using the product rule, we would end up with a dr dt and a dH dt. But the only rate of change that is relevant to us is dH dt. You can always tell by your rates of change what you want in your final function. The only variables are volume and height, which means that this formula can only have in it volume and height. So somehow we have to eliminate the radius r. Well, the key is we're told that there's a relationship between them. As the sand piles up, the height of the sand pile will always be 1/3 of the diameter. So this right here is giving us the relationship that we need. So we need to eliminate this r. So first of all, we need to replace diameter with radius. So the height would be 1/3, and then a diameter would just be 2 radii, so 2 times r. So the height is always 2/3 the radius. We need to, however, eliminate the radius, so we need to solve for r. So if we just divide both sides by 2/3, we will get that the radius is always 3/2 of the height. As this cone piles up, the height and the radius are changing, but they're always in the same proportion. The radius is always 3/2 of the height. We can now take that quantity and substitute it into here to eliminate the radius. And again, the way you know to do that is by looking at your rates of change. If there had been a dr dt in the question, we would have kept it there, but we can't have it. So what we need to do now is rewrite our volume formula. Our volume formula will be 1/3 pi, and instead of putting radius, we're going to put 3/2 height squared times the height. We now have a function where volume depends only on height, which is exactly what we need. We could differentiate that formula in its given state, but that would be very difficult, product rule and everything, so it's best to tidy that up a little bit. So what I'm going to do is I'm going to actually square the 3/2, which will be 9/4, and the 9/4 multiplied by the 1/3. So we're just, well, maybe I'll just do this for you. So we're going to go 1/3 pi times 9/4 h squared h. The 3 goes into the 9 3 times, so we're just going to get 3/4 pi h cubed. So we've created now a brand new formula, and this formula gives us the volume as a function of height. Now once we have that, the rest of it's just the differentiating. So we differentiate with respect to time, so dV dt equals, the 3/4 pi is a constant. The derivative of h cubed is 3h squared times the compensating term dH dt. Now we need to know whether we have the appropriate values. We have dV dt is 180, so dV dt is 180, 3/4 pi times Now, however, the question requires us to know the height. We don't know the height. We were given the radius. But of course, the radius and the height are related. So the radius was 6. So 6 is equal to 3/2 the height. So the height would be 4. Just multiply by 2 and divide by 3. So this is going to be 3 times 4 dH dt. Now the rest of it is just solving for dH dt. You can just use a calculator if you want. I like to work it out in the exact form. This 4 squared is being divided by 4, so I can divide out that 4 with that one. And so my dH dt is going to equal 180 divided by, and on this side we have 3 times pi times 3 times 4. So 9 times 4, so 36 pi. So we end up with 180 divided by 36 pi, which we can reduce. 36 goes into 185 times, so we end up with 5 over pi. And I don't think I changed that to a decimal, so I'm going to leave it as 5 over pi. Again, you can change it if you want to 5 divided by 3.14. It really doesn't matter to me. The units would be height over time, so this would be centimeters per hour. Sorry, meters per hour. So that's how fast the height would be changing. So that wraps up our study of related rates, and that wraps up Chapter 5. So the next video will be a review of Section 6.6, where I'll talk about the test and do a little bit of review with you and hopefully get you going in preparation for your Chapter 6 exam.